In this video, let's solve a couple problems relating to maximum power and Thevenin equivalent circuits. So part A of this question says, find the value of RL such that you get maximum power transfer into RL. The condition that makes that happen is when RL is equal to R Thevenin. So let's go ahead and find what R Thevenin is. And while we're at it, let's calculate the Thevenin equivalent circuit. So to do this, we first need to find the voltage of open circuit. So across these terminals, what's this open circuit voltage? And to do that, we can do that pretty easily using a voltage divider. So we do 360 going in multiplied by the resistor of interest, which is 150, divided by 30 plus 150. And this gives us, let me plug that into the calculator real quick, 360 times 150 over 180 is equal to 300 volts. And then let's go ahead and calculate the short circuit current. I short circuit is equal to this current flowing through here. If all the current's flowing through this, none of it's going to flow through there. So we just need to find the current through this 30 ohm resistor. And that's going to be I equals V over R equals 360 over 30, which is equal to, I think 12, right? 36 over 3 is 12. My teacher says 36 over 3 is 12. Yeah. My teacher always says 2 plus 2 equals 4. But make sure with your calculator, just to be sure. And with these two things, we have R Thev equals V open circuit over I short circuit. So we get 300 over 12, and that's equal to 25. So our equivalent circuit looks like this. We have 300 volts, and R Thev is equal to 25, and we have A and B. So our RL equals 25 ohms. Awesome. So I'm going to go ahead and erase all this, and we have our answer for part A. Let's remember our V open circuit was equal to 300 volts, and we have an equation for maximum power transfer. So B, find the maximum power transfer. So that's going to be equal to V Thev squared over 4RL, where RL is equal to R Thev. So this is going to be equal to 300 squared over 4 times 25, which is equal to 300 squared divided by 4 times 25 is equal to 900 watts. And now part C, when RL is adjusted for maximum power transfer, what is this percentage of power delivered by 360 volt source into RL? So we need to find the power of the 360 volts. So that's going to be a quick calculation. We got 360, there's a 30 here, 150. We loaded it up with 25. So we want to find the current here, I source. So to do that, I source is equal to I150 plus I25, these two. So we need to find what those two are equal to. To do this, I think there's a couple of different ways to do it. For me, it's easiest if we went ahead and did a simplification. So we did 360 and then 30 and some REQ. This way we can find the voltage drop across REQ, which will be the same voltage drop across these two. And that'll allow us to find I150 and I20 pretty quickly. So we'll use voltage divider again. But first, let's find 25 in parallel with 150. That's 25 times 150 over 25 plus 150. And this is equal to 150 over 7. So the voltage divider looks like this. It's going to be V of REQ is equal to 360 multiplied by 150 over 7 divided by 150 over 7 plus 30. And if we want to plug that into our calculator, we get VREQ equals 150 volts. So we know this plus minus thing right here is 150. And solving for I150 is V over R. 150 over 150 equals 1. And then I have 25 equals 150 over 25, which is equal to 6. So we have in total IS equals 7 amps. So using the passive sign convention, we get 360 times 7 amps, and it's negative because we enter from the negative terminal, and this is going to be equal to 360 times 7 is 2520. So the last part of this question is to find the percentage of the power delivered versus the power absorbed by that load. So we have it absorbed was 900 watts, and how much it's being delivered is 2520. Multiply this by 100%, and this gives you 35.71%. So that's how much of our voltage source we're able to give power to this resistor, and that's the maximum. You can get this out of this circuit configuration. So that's pretty cool.